Let's try one more example. So we've got this curve here that we want to find a piecewise smooth parametrization. So it starts at 0, 0. It goes up to the point up here would be, oops, not 1, 0, 0, 1. And then it follows a parametric path, or sorry, a parabolic path down to the point 1, 0 before it heads back to 0, 0. So again, this one I probably would also split into 3 curves. Curve 1, curve 2, and curve 3. So let's take a look at each of those. So let's look at curve 1 first. So we need to go from 0, 0, and then we just need to go straight up to the point 0, 1. So again, let's let x of t's just stay constantly 0, and let's let y of t just be t, and therefore that would mean that t needs to start at 0 and go to 1. So then for curve 2, my t values are going to have to start at 1 and go to something. Now notice that this one needs to go from that point at 0, 1 down to the point at 1, 0, but it needs to follow that parabola, which is in rectangular coordinates, it's y equals negative x squared plus 1. So we have to follow that parabolic path. So again, we're going to need an x of t, and we're going to need a y of t. Now, if you remember when we did parametric equations, one of the easiest ways to just come up with a parametrization was to if we had an independent variable in rectangular coordinates, just let that be t, and then let the y function just be the same function that we had, where now we just replace the x with whatever we let x be. Now the problem in this one is that what we're going to get if we let x of t be t, I have to let t start at 1, which would mean that x is starting at a value of 1, which is not what I want. Instead, I want x to go from 0 to 1. So we want it to increase from 0 up to 1. So we need to edit that guy to make it do that. So then essentially, that x component we could view linearly. So we could try and create x to go from 0 to 1 linearly. So maybe then we take it and we say, well, it needs to increase. So we could take t maybe. When t is 1, I need the x value to be 0, so maybe we'll subtract 1 from it. And then if I let t go up to 2, well then by the time I hit 2, x of t will end at 1. And then what we can do is then, so x is going to essentially follow that increasing from 0 up to 1, and then to make the y coordinates follow that parabolic path, we just plug in whatever we let x be down here. So y of t is just going to be negative the quantity t minus 1 squared plus 1. So then we're on our third curve. T needs to start at 2 this time, and we need to again go from 1, 0 to 0, 0. So x of t and y of t. Well, y is just constantly 0 this whole time. So we could just let y be constantly 0. And then x needs to decrease starting at 1, going down to 0. It's a full unit length of 1 across the whole thing. So maybe we'll let t stop at 3. And then to go from 1 down to 0, this is similar to the last one, perhaps we'll do 3 minus t. That way, when we start at a t value of 2, 3 minus 2 is 1, and by the time we get to t equals 3, we'll be at 3 minus 3, which is 0. So then my function, we can have our, say, r of t being a piecewise function, where again, let's put it in terms of I and j. So curve 1, there is no x component, it's 0. and then we would have t times j. That one was for t from 0 to 1. And then my next one, I've got t minus 1 times I. Oops. Let's write it correctly. Plus, we've got that negative the quantity t minus 1 squared, all plus 1 times j. If you wanted to simplify that, you could. It just doesn't really matter. And so that's for t from 1 to 2. And then we want the third one, the x component is 3 minus t. So that's times I, and then the j component is 0, and that goes from t ranging from 2 to 3. So my full domain of this would be t goes from 0 all the way to 3. Both of the examples that we did were for plane curves. You could do the same thing if we had something in 3 dimensions. So you can just take these same ideas and scale them up if you want to do 3-dimensional parameterizations.